So it's really good that we have just done transformations fairly recently, because this should be easy peasy, right? So what I want you to do here is we're going to describe and draw an example of the following transformation vocabulary. What's like the baby word for translation? Slide, right? How could you draw a picture of that? So maybe if you have a parabola, what's a slide? Oh, it's up here now. Right? That's what I mean by kind of draw a picture of it. Just so you kind of have it fresh in your mind there. What is kind of that baby word for reflection? Flip. Again, remembering the SL for slide and the FL for flip. I don't know, draw your own picture. I'm going to kind of do this. If I have one here, a flip might look like that. So it's a reflection over some line. Rotation. What's that baby word? Turn. Again, the T for turn. So this is what I'm starting with. Pre-image. Maybe one like this. That would be a turn, a rotation. And then dilation. I don't know if we had any baby words for that. You're making it bigger or you're compressing. We say enlargement or compression. Sometimes instead of enlarge, we say stretch. So I think we did, well, like a circle. So a dilation might be it's bigger or maybe it's smaller. So you just have a little visual of it. Not a big deal. Well, we just want to have these words fresh in our minds. Okay. So we're going to go back to this notion of parent functions. We talked about this a little bit last time. We looked at x squared and we applied some different kinds of transformations to them. But we have to know parent functions in order to get these different transformations. So x squared, I think we're familiar. So you can use the, this guy, because it's pretty easy. You would just say, okay, whoops, wrong button. That's the wrong button. Here it is. So you press x squared, and you can see it. So you know what it looks like. But think about how you would do this manually. And remember, we talked about the table of values method. I'm going to kind of do that table of values method in my head. So if you start at 0 and you plug 0 in, what do you get for y? 0. If you start with 1, what do you get for y? 1 squared? 1. Well, what about negative 1? Same thing, right? So what if I get something on this side, I'm going to have it on the other side. What about 2? Just 2. If x is 2, 4. 1, 2, 3, 4. X squared. And I'm going to have a matching point on the other side. We'll go one more deep. So we did 1, 2. What's 3? 3 goes to? Oh, 9. Now I can barely see this to count here. Let me see here. 1, 2, 3, 4, 5, 6, 7, 8, 9. There'll be a matching one on the other side. So there we go. Now where are the zeros for this thing? At x equals 0. Okay, and that's what x squared looks like. We're very familiar with that. Now I've got a cubic here, x cubed. We're a little less familiar with this because we don't really work with them in Algebra 1. We're going to be working with them more in Algebra 2. We're going to do the same thing. So when x is 0, what's y? 0, right? You plug the 0 in. How about when x is 1? 1 cubed, 1. Now how about negative 1? When x is negative 1, what is x cubed? Negative 1, because negative 1 times negative 1 times negative 1, we get that negative sign. Let's go over to 2. When x is 2, what's 2 cubed? 8. So I got to find 8. I think that's over here. What about when x is negative 2? Down here. Negative 2 times negative 2 times negative 2. Negative 8. So I'm here. It looks kind of like this. Where's the 0? That's 0 again. And of course you can put this in the calculator. So we looked at x squared. Let's look at x cubed. So whoops, let me just clear this out. X, you know how there's that little circumflex above the divide? That's how you raise to that exponent. So that looks like what we got, doesn't it? Interesting thing now, just to kind of play with this a little bit. Do you know what x to the 4th looks like? That parent function? Well, let's see. Looks a bit like x squared, doesn't it? Well, what does x squared look like? Let's compare them. This is just kind of an interesting thing here. The first one's x to the fourth. Here's x squared. Huh, what about x to the sixth? Well, what about x to the sixth? Oh, what about x to the eighth? What do you think's going to happen? Yeah, but it basically looks like x squared, doesn't it? They all kind of have that same parabolic shape. They just get a tiny bit narrower. So anything with a parent function of x to an even number kind of looks like this. Now what about x cubed? Let's see what happens with that. I'm going to put my x cubed back. X cubed. And let me get rid of some of this stuff. X to the fifth. Now I'm working with odd numbers. There's x cubed. There's x to the fifth. What do you think is going to happen with x to the seventh? Yeah, right, we're going to get that similar looking thing, maybe slightly narrower. So it's nice to know what these parent functions look like. So anytime you have something to an even power, it kind of looks like this, and anytime you have a parent function to an odd number, it kind of looks like that. 0 at 0. Interesting. All right, now square root x. Whoa, okay. Let's think about this now. Let's go to 0. When x is 0, what's y? 0, right? Square root of 0 is 0. When x is 1, what's y? 1. Now when x is negative 1, now my domain is all real numbers. What happens if the square root of negative 1? Can't do it, right? I can't have this for in the real number system, so my domain is going to be restricted here to x bigger than or equal to 0. So that's all I'm going to be worried about for these, because I can't. In the real number system, it won't let me look at that. Okay, so I'm going to ignore my negatives. Now I did 1. Now 2, square root 2, I don't really know what that is. Do I know? I mean, it exists. Do I know what the square root of 3 is? Sort of, 1.732. George Washington's birthday. But what about the square root of 4? I know that one, right? So I think what I'm doing, I can pick the domain. I can pick the test points I want. So I'm going to go to 4 now. So 1, 2, 3, 4. When x is 4, what's y? 2. So I'm only going to pick x's that are kind of easy to take the square root of. So 5 is not easy. 6 is not easy. 7, 8, 9 is, right? So my next x I'm going to pick is 9. Square root of 9, 1, 2, 3. So can I see what's happening here? Oops. But it's curved. It is a curve, and you know this is something you can look at on the calculator. So let's do that. Clear that. Clear that. So I want the square root of x. Square root of x. Did I miss it? No. Okay, so that's what it looks like. It is curving. It just grows very slowly. Because, you know, think about that. You know, when's the next point? I have to go all the way to 16 before I can move up to 4. And I have to go all the way to 25 before I can move up to 5. So it's kind of a slow-growing graph here, and its zeros are, and x is 0. What does cube root look like? All right, let's think about that guy. Starting at 0, what's the cube root of 0? It's easy, right? Cube root of 1. Well, that's kind of easy. Looking at negative 1. Cube root of negative 1. Can I take the cube root of a negative? It's negative 1. Because negative 1 times negative 1 times negative 1 gives me negative 1. Oh, so this one this can be all real numbers. Let's see. Cube root of 2 is too hard. What's the next cube root that's kind of easy to find? All right, cube root of 1. Yeah, I can do that. 2. Cube root of 2. Cube root of 3. What's my next perfect cube? 8. So let's take the cube root of that. So I have to go all the way to 8. 1, 2, 3, 4, 5, 6. I think I'm here. Cube root of 8 is 2. And then I can go to negative 8. I think that's here, and get negative 2. So this one kind of looks a little bit like the square root of x, but it's even slower growing. Now it is getting bigger, but I also have kind of another image of it. I missed a little bit here. Over on this side. Cube root of x. And I'll put that in here so we can see it a little bit better. So clear that guy out. Remember where cube root is, right? You press the map button, it's number 4, put in that x. Okay, parent function. Look at one more parent function, which is, what is that thing? Absolute value. Absolute value of x. All right, let's put in some points. So the absolute value of 0, 0. Absolute value of 1, 1. Absolute value of 2, 2. So on this side, it looks a lot like y equals x, doesn't it? I'm trying to find my points here. Now what happens though when x is less than 0? So let's see, if x is negative 1, what's y? 1. What's the absolute value of negative 2? 2. So on this side, it looks like y equals negative x. I'm having trouble with like a little optical illusion here on me. Okay, so bounces right back up. Whoops. So that's what absolute x looks like. Okay? And the 0 is at 0, and I can't remember if I put that on this one or not. Yeah, 0 is at 0. All of these just go through 0. That's their only x-intercept for these graphs. So if we are able to kind of keep a picture of these different things in our minds, these different parent functions, we can get an awful lot of graphing done. So let's look at the next page here and see what I have to say. I think there's just a little bit from the bottom. This is just in the bottom of page 1. These are parent functions. We call them function families. And we kind of apply different transformations on these parent functions to graph different things here. So going now to page 2 here, here's what f of x equals x squared looks like. So if you want to put that in your graph again, remember how to do it by hand. 0 is 0, 1 squared is 1, going to have a match on the other side. 2 squared is 4, I'll have a match on the other side. 3 squared is 9, you'll have a match on the other side. So you just want to have that kind of graph in your mind. What is y equals x squared, or f of x is x squared, parent function. Okay. So we're going to graph some different x squared type functions, and we're going to figure out what kind of transformation is taking place. So let's see if we can sort of do this. Maybe like, it's still the table of values method, but sort of in our head a little bit. So if x is 0, what is y? We plug in a 0. 0 plus 3. 3. Now when x is 1, what happens here? We get 1 squared is 1 plus 3, 4. Let's try negative 1. Well, negative 1 squared is 1, just like the other one, just like 1 is. So we're going to get the same thing. It's starting to pop back. You can see that symmetry starting. How about when x is 2? 2 squared is 4, plus 3 is 7. 1, 2, 3, 4, 5, 6, 7. And because negative 2 squared is the same as 2 squared, we will see the same thing on the other side. If we go one more, I think we might be off the graph. 1, 2, if we do 3, that's 9 plus 3, so we'll be up here a little bit, but we'll have the same point on the other side. Whoops. Now, graphing that little thing here. You see do you understand what I'm doing when I'm doing table of values in my head? I'm basically saying, let's pick some points and see what's happening, and I'm plugging it in as I'm going. That's all that I'm doing here if you're having a little trouble following that. So can we figure out from this to this, what kind of transformation was that? Yeah. A translation. Was it a translation up, down, left, right? Could we describe it a little bit more? Up. It's translated up. We basically take this graph and we shift it up using what's called a vertical translation, because I'm just going up in a vertical direction. And it's 3 units up, which matches this 3. Shift up 3 units. Can't hurt to say that. Okay. Let's try it for this other guy here now. It's x plus 3. Now how is this different? At first you may think it's the same thing. X squared plus 3 versus x plus 3 squared. Right? So we're adding the 3 and then squaring it. Here we square and then add 3. So at 0, what happens? So 0 plus 3 is 3. 3 squared. So at 0, we're at 9. I think that's here on this little graph. Right? Now, how about 1? 1 plus 3 is 4. 4 squared, so we're like way off the graph. We're like way up here at 1. So, let's try negative 1. What happens at negative 1? 4. Negative 1 plus 3 is 2. 2 squared is 4. I'm liking, let's go in this direction because I'm off the graph already with this one. How about negative 2? Negative 2 plus 3, 1. 1 squared, 1. And let's try negative 3. Negative 3 plus 3 is 0. 0 squared. Okay. What about negative 4? Negative 4 plus 3 is negative 1. But when I square negative 1, I'm going to pop back up, right? I think I'm here. Then I can try negative 5. Negative 5 plus 3 is negative 2. Square that, you get 4. Can we see what's happening now? What's this one going to be? 9. Whoops. Missed a little bit with my little slave here. Let me see if I make it a little bit better. It's an upside down roller coaster. Well, let me ask you this. This shape, this shape, this shape, generally speaking, if these are translations, remember translations are isometries? They are congruent, yes? What's the only thing different about them? Where I slid them around on the graph, right? So they really are the same thing slid around on the graph. Now what kind of translation? Now it is a translation, right? But what happened? Based from where we started as our parent function, what did we do to this thing, Sarah? We went left. How many units left did we go? Right? Normally we're here. 1, 2, 3. So we shifted left 3 units. And that was used, we used a horizontal translation. Is there a question over there? No? Right, we just did. Okay. A couple of other ones to try, at least for x squared here. Oh, I got a bunch more for x squared. But let's see what x squared minus 3. Now, based on what we've seen so far, can you make a prediction here? What do you think it's going to look like? What do you think, Alex?
It's going to start on negative y and 0.
So my 0 when I go to negative 3. And then what do you think is going to happen? Yeah, so over here at 1, 1 minus 3 is negative 2. And if I go to negative 1, well, I'm squaring it, it gets to be the same value, right? If I go to 2, that's 4 minus 3. That's 1. These are really tiny. I'm having a little trouble seeing it. Here. I think. 1, 2. Oh, I'm sorry, 1 comes up here. Right? A little mistake there. Let's see, if we go up to 3, so that's 9 minus 3 is 6. And I'll have one on this side, and so on. So what happened? What kind of a transformation? It is still a translation, but what kind? Like what happened? Yeah? Yeah, I shifted it down 3 units. Compare that to the shift up. All right, what's the difference? This minus and this plus, and this is still a vertical translation. So this minus 3, this appears to be something that moves it up and down. What do you think is going to happen with this one compared to what happened with the x plus 3? What do you think, Tyler? Yeah, we think, right? He's predicting, well, since the plus went to the left, maybe this one goes to the right. Let's just try a couple of points. So at 0, what do you get there? Minus 3. Square that, you get a 9. That's up here. If I go more negative, it's going to get bigger on this side. Let's try 1. 1 minus 3 is negative 2. So square that, you're at 4. At 2, You get 2 minus 3 is negative 1, square that. 1, 3, 3, that's your 0. And we're going to bounce right back up again. Okay. That was a terrible connect the dots, but I think you see what I mean here. Oops. So you're right. Didn't we start? Again, you're thinking about where is my parent function and what did I do to it? I shifted it right. 3 units, and I have a horizontal translation here. All right, let's see. 3x squared. Now, we looked a little bit at this. When you put a number in front, what happens if this number is bigger than 1? Do you remember, Alex? In what way does it get smaller? Skinnier, right? We do that stretch to it. So again, if it's 0, it's 0. But if it's 1, instead of bouncing up to 1, it's going to be 3. And same on the other side. When you're at 2, 2 squared is 4 times 3. We're already off the graph. So we're getting like a much skinnier, whoops, a little trouble here with my slate today. But you get a much skinnier one compared to this, compared to y equals x squared. So this one, it's a dilation, it's a stretch. We're stretching it by a factor of 3. Yeah, let's try, are we ready for the next one? Some people still doing it? All right. The next one is going to be f of x is negative 3 squared. What do you think is going to happen now? We looked a little bit at this last time. Yeah, Tejas?
It'll be the opposite.
Opposite in what way?
Of
A flip, which was our grown-up word for flip. You could look, you could look. Reflection. This is going to reflect it across the x-axis. Let's make sure. So if you put a 0 in, it's 0. Now if you put a 1 in, that's 1 times negative 3. So now we're going this way. And there'll be 1 on the other side. 2 squared is 4. And again, we're already off the graph, but now we are down here. So we're going to get that skinny thing. So not only are we dilating, but we're also reflecting. And it's going to be across the x-axis. So 2 things. What's going to happen with this guy? When this number is between 0 and 1, and we looked at it tiny, we looked at it real quick last time. Do you remember what happens? You know, we can just try it. Do you remember, Alex? It gets wider, it gets a little flatter. So 0 is still going to be 0. Now I'm going to be careful here. When I square it, I want something divisible by 3. So 1 is probably not a good choice. 2 squared is 4/3. I don't like that one. Let's try 3. 3 squared is 9. Divide by 3. Okay, so 1, 2, 3. 9 divided by 3 is 3. 1, 2, 3. And then it's going to be a match on the other side. These are tiny, these little things. Oh, okay, 1, 2, 3. 4 is too hard. 5 is too hard. 6 squared. We could do 6, right? 6 squared is 36 divided by 3. 12. So what happens here? That's at 6. 1, 2, 3, 4, 5, 6 is somewhere over here. So we're flatter. Whoops. Then what? Then the parent function of x squared. We're always comparing it to x squared. This is a dilation. It's a compression. Dilation is the correct word. A compression by a factor of 1/3. We're pressing it down. And so what do you think is going to happen here? This compression and flip. So we can put that one in here. We can do 3. 1, 2, 3. It's going to be 1, 2, 3. Same one on the other side. And so forth. So not very good. A little trouble here with the slate. Okay, so, but again, this one is a dilation as well as a reflection. Your pictures will be better. It is hard using this little thing. And you can always compare it on the calculator, okay? So, okay, so we just did a bunch of things playing with x squared. Let's see if we can kind of draw a few conclusions here. I think we can. I'm thinking about our observations here. So the first question, what kind of transformation occurs if we add or subtract a constant to a parent function? So for example, x squared plus 3 or x squared minus 3. What kind of transformation do you get? Yes, sir. A translation. And this was the one that moved up or down, right? So I'm going to call this a vertical translation. I have this, I don't know if this works here. Let me see if this works. Okay, I've got my little keywords. See how cool that is? For me, I don't have to write it, but you do. Okay. Now if we add a constant, it will shift, using my little words here, up. And if I subtract a constant like this one, it will shift down. I'm saving myself writing. Of course you do that. Makes sense, right? Questions on that? Let's see what conclusions we can draw with this one. So look at your x plus 3 squared, compare it to x squared. This transformation is a horizontal translation, right? Going this way. Now if you add a constant, the function will shift, look at your picture, left. And if you subtract a constant, if this was x minus 3 squared, which way did it shift? Right. Might be just a little confusing about that. Does nobody finds that confusing? Because I do. Sarah, what do you think? Positive, you're going to want to go this way, right? Negative, you're going to want to go this way. But it sure feels backwards, doesn't it? It does. It feels backwards. But it's not. So you kind of have to resist that urge so when you see a plus to go right and a minus to go left. Think about like the 0, you know, it's kind of backwards. Okay, so remember that's an important kind of note there. And then finally, what kind of transformation occurs, not finally, almost finally, if you put a negative up front? If you negate it, what happens? And I got my words here, I got my word bank. What kind of transformation do you think we get, Alex? There you got that. We got the lovely little word bank there. Reflection over the x-axis, right? Because it's just going to flip it. And if you have a negative, you make it positive, flips it back. And then I think now I can say finally, what kind of transformation occurs if you multiply by a constant up front? Look in here. What happens? Dilation? Yep. And then if you multiply by a big number, the magnitude bigger than 1, it will, I'm looking at these words, stretch. Whoa, I didn't need to press U, I want to do it. Stretch. And then what about if you multiply by a fraction, a proper fraction now? Yeah? Compress. Okay, so let's keep those notes handy because knowing this, we can do a lot of graphing sort of fairly easily. So we're getting there, my friends. It looks like a lot of paper here, but we are getting there. So if I'm looking at this one now, given the observations that we just made, can we predict what this thing's going to look like, x plus 5 squared? Let's talk about it first. What do you think that's going to look like? Going left how? What? What am I starting with? I'm starting with the parent function x squared, and then what am I doing with it? You said going left. How many units? 5. So normally, right, when we graph y equals x squared, we start over here. So instead of starting at x equals 0, shift it left 5. 1, 2, 3, 4, 5. I think I counted that right. Little tiny boxes, terrible old eyes. And then you're basically doing y equals x squared from here. So if x is 1, it's 1. And you'll have a match on the other side. When x is 2, it's 4. 1, 2, 3, 4. And there's a match on the other side. When x is 3, 3 squared is 9. And I'll have a match on the other side. So basically all I'm doing is I know how to graph y equals x squared. It's pretty easy. And I'm just doing it, instead of at the origin, I'm doing it over here. Does that make sense at all? Yeah? Did I have to find the axis of symmetry? Did I have to, what's the vertex? Did I have to find the 0? Did I have to do any of that? I know what it looks like. I've got that field. Bang, it's right there. What about this one now? It's x squared plus 5. What do I know about the transformation that's going to occur? Yeah, going up 5, right? So that means I start at the origin because that's where my parent function starts, and I'm going to shift up 5. And now from here, I'm just going to graph y equals x squared as if this was the origin. So if this is 1, that's 1. And I'm going to have a match on the other side. If this is 2, then this would be 4. Oh, did I count it right? 1, 2, 3. That's up here with a match on the other side. You know, basically there. I don't need any of that other stuff that we're spending like hours finding and struggling with zeros. I know what it looks like. Let's try a couple of other ones. Any questions? Let's see what we got here. Negative 5x squared. So what's going to happen here? It's going to be a stretch. What else? Is it going to go right? Reflected over what? Yeah, so it's going to be an upside down flip. So normally x squared starts here, so I know it's going to be upside down, and I know it's going to be skinnier. So I know 0, 0, and 1 is just going to be 1, 2, 3, 4, 5. And then I can just see it's going to be really skinny, and I can just kind of figure it out. Whoops. Very skinny. Quick. No fuss, no muss. What do I know is going to happen to this guy? What? Parent function, but compressed, right? Flattened out a bit. So I probably only just need a couple of points. I'm going to start maybe at 5. 5 squared, 25, divide by 5, it's going to be 5. So 1, 2, 3, 4, 5, and the same thing on the other side. So the idea is quickly being able to sketch, having a really good idea of what this looks like. Are there questions so far? Yeah? Okay, this is not on here. We're just going to kind of do this little exercise here. Just to review, we had some new functions. So let's see if we can match these. We have some new things that we looked at. Which one of these is x cubed here? If I'm going to move this guy. So where is that? Tell me where. Here? This one. Oh, okay. How about absolute x? Oh, where does he go? Where does he go? Oh, here he is. Square root x, square root x. Right, remember this one I can't have any negatives because I can't take the negative of square root. And then what about this guy? What's this guy? There's my x squared. Oh, little ringer there. So if we can remember these little pictures, we can apply all those same transformations to these. You barely know anything about these graphs, and you can graph them. So let's try a couple of these here. These ones are, where is this? I think I'm missing one. Did I miss a page? Oh, it's over here. They're just out of order, I guess. Oh, no. Okay, I see what you did here. So the one that I did the matching, I did it. You were supposed to kind of sketch it on that page there. So if you see on the top of page 4, just re-sketch those graphs. Okay, so you copied these graphs down so you have those pictures right in front of you so that when we kind of work on these, do you think the transformation observations we made earlier will apply here? Do you think? Yes, yes. They will, yes. So, predict what the remaining functions will look like. So if I have x plus 2 cubed, so what do you think is going to happen? Now that parent function of x cubed, yeah, kind of like that, right? What do you think is going to happen if x plus 2 is here? Careful. Shift it left 2 units. So it's basically going to be this thing, but now it's over here, right? So let's see. So if I'm normally starting at 0, 0, I'm going to shift left. That's where I start. And now I graph x cubed starting here. So that's like 1. 1 cubed is 1, and then the negative will be below it. This is like 2 relative to that. So 1, 2 cubed is 8. So 1, 2, 3, 4, 5, 7, 8. I think, I don't know, I may have counted wrong, but they're going to be the same match on the other side from here. 1, 2, 3. This is so hard to read. These are teeny tiny, but I can see what's happening. Shifting it left. Whoops, missing. Shifting it left 2. I missed a little bit. Shift left 2. That's what this means. All right. So it's like whatever this shape is, just move it. Radical x minus 2. All right, now I'm going to remember what radical x is. There's like this one, right? It's a very slow growing kind of curve like that. So what does the minus 2 mean here? Shift it what? Well, is it in parentheses? Oh, it's the whole parent function minus 2. What happens? Did I hear bell ringing? Is that just me? Is my trouble? Do we need to call 911? No, okay, that's not me. Good. There's bells ringing over in science. Having fun. What do I do here? Well, let me ask this way. This is my function. It's kitty cat minus 2. What am I going to do to kitty cat? We're missing the big idea? Move it down 2. I don't know what kitty cat is, doesn't matter, but I'm going to move it down 2. So square root x, what am I going to do with it? Move it down 2. So shift down 2. So square root x normally starts at 0, so I'm going to shift it down. Now I know like 1 square root of 1 is 1, so I'm regraphing that thing from here. Now square root of 1, the easiest thing now to find the square root of is 4. So from here I'm going to count over 4. 1, 2, 3, 4. And the square root of 4 is 2, so I'm hitting it here. The next square root that's easy to find is 9. So I guess I'm here, 1, 2, 3. And so I can kind of see where it goes. Shifting it down. Interestingly enough, now if this was, and I don't have one like this on here, if this was square root of x minus 2, what would that do? You'd start here and shift right. If it was square root of x plus 2, I'd start here and move it left. So it looks like I've got negatives. They're okay if it's x plus 2. So helps me graph. Let's try some of these other guys. And it's still yes. It's the same question. It's still yes. Negative cube root x. Seriously? All right, well, let's think here. Cube root x, we have that little picture. That's something like this, right? Cube root x. What's negative going to do to it? Yeah, that's my reflection, right? So if you're up here, you're going to be down here. And if you're here, you're going to be up here. So I know what it looks like already. So at 0, so when I took the cube root of 1, I put it up here, but I want to be down because I'm reflecting. When I took the cube root of negative 1, it went down here, but I'm going to reflect it up. Cube root of 2, can't do that. 3, 4, 5, 6, 7, 8. Cube root of 8 I can do, and I'm going to flip it. Instead of saying 2, I'm going to say negative 2, and I'm going to do the same on the other side here. And re-get that. Reflected, reflected. This is a reflection. Now we can combine more than one thing. Nobody says, that you have to do it all at once. So what happened in here? What are some of the things that are going to happen here? Yeah, Tyler. It's going to stretch, right? We're going to see that dilation by a factor of 2. Okay, that's this, right? What's this going to do? Going to shift it right once. And what's this going to do? Shift it up 1. Wow. So we have 3 things to do. Let's remember what our parent class kind of looks like, our parent function, I should say. It looks like this, right? So when I'm at my 0, right, I have to shift it right 1, and then I have to shift it up 1. So I guess I'm here. So once I know where I'm starting, I'm kind of okay. I'm just going to work now with this 2. So the absolute value of 1 is 1, except that I'm multiplying it by 2. So negative 1 will match the same way. It's not 1, it's 2. But I'm starting from here, and I'm counting 1. Now if I were to go to count 2, the absolute value of 2 is 2, except I'm multiplying by 2. So it gets a little bit narrower. There'll be a match. So it's more of a skinny. Whoops. It's a skinny one of these, a little bit skinnier, shifted right 1 and up 1. And again, we've never worked with these graphs before. We've never worked with most of these functions, and we can graph them pretty easily. So transformations, good things. That's why we went through the pain this year to learn them. Yay, there was a reason. Yes?
Isn't it basically in vertex form?
Yes. So yes, the observation he just made is, remember vertex form? So of a parabola? So the beauty of this form now is not only do I know the vertex, which is what's the vertex for this? 2, 3, right? So if I have a graph, I know I go to 2, 3. because I shift right 2 and up 3. And now I draw a parabola, except it's going to be a skinny one. So I know, like almost doing nothing, what this thing looks like. How much easier is that to graph than what we've been going through? Way easier. You have now a feel of what these things look like. Excellent observation. So that's why we went through that vertex form. This one is also kind of interesting. It says, what's the equation for this guy? So what you do is you say, well, gee, what transformations took place? First of all, what's the parent function? Parent function is y equals x squared, right? I recognize the parabola. What did I do to it? Well, it's reflected. First thing I'm noticing, so what does that mean? So now I'm up to this. What else do I know? I shifted left 2. So what does that do? Careful, careful. That's a plus, because it's like opposite than what you want it to be. I don't think we have any dilation on it, but you can check. So if you go 1, it should only be going up 1, and it looks like it is. So I would just kind of, when you go 2, it looks like it's going up 2. So I did that quick kind of check. I don't really see a dilation being applied. There it is. Look how quickly you can write the graph of that particular equation. You couldn't do that before you walked in here. Is that hard? The key thing is, I think the hardest thing is that when you go this way, that's a plus. When you go that way, it's a minus. It really is opposite than what you wanted to say. So the last thing I want you to do here is I kind of want you to write this in your own words, because that's how you're going to remember it. So in your own words, summarize the observations we've made about graphing with transformations and use examples to help you write your notes. So, I mean, you know, what I put, these are my words. So for horizontal shifts left and right, you add to shift left. That's kind of an important thing to note. And you subtract to shift right. And here's my example that I put. X minus 2 squared shifts right. And that's all I mean by that. You can use my words. It's better if it comes from your words.